but it's actually about 1 trillion stars that are 2 million light years away. The light from those stars has been traveling to us for 2 million years. So when you look up in the night sky, you don't see anything that's happening now. You're actually looking into the past. And the farther something away is, the farther into its past you're looking. How cool is that? It's like the coolest idea. And the problem is that no information can travel faster than the speed of light. Like, how do you communicate with someone, right? You either talk, which is a local phenomenon, or you have to send some sort of wave, a radio wave or a microwave or a light wave or a gamma. All those are the same speed, right? But if nothing can travel faster than that, then that's the only way you can exchange information is by a wave. Or by seeing it happen. Okay? So what they found out in the early 1900s was something really weird happens. Okay? Something really, really weird happens. Is that if you want to measure the speed, or you want to like increase something's speed, you just push harder on it. True? Okay? So you're going to push harder, and so we're going to do more work. Work is equal to the force times the distance, right? And this is going to be equal to the change in the energy, yes? Does that make sense? And so we're going to increase our energy down here. Basically, it's our kinetic energy. Right? We're going to do more work here. And what happens to the speed? It should increase, right? If you're putting more force on, you're adding more energy, it should increase, and it does. Except for they found out there's a huge problem. And they found out there's a huge problem, and that as you start to get closer to the speed of light, no matter how much force you apply, no matter how much more energy you add, no matter how much more you put into it, actually the speed levels out and it approaches the speed of light asymptotically. Even if you keep putting more and more and more energy in, it cannot get any faster. And here's actually what happens, which is fascinating to me, is if the work we do goes into changing the kinetic energy, we keep putting more work in, and initially the speed increases. But then something shocking starts to happen. Is all this work you do starts to make the mass get bigger and bigger. Spontaneously, the mass just starts to increase. And so that actually makes it even harder, because if you're trying to put more work in and the mass goes up, then it has more inertia, it's actually harder to get it to move faster anyway. That's why we get this asymptotic thing, because all this energy we're putting in goes and the mass starts to spontaneously increase. Yeah?
Does the mass ever decrease?
Yeah, slow it down. And the mass goes back down. So you'll hear about like super colliders, right? Where they're going to take protons and they're going to speed them up, and then crash them into something else. Well, they keep putting all this energy in and they get faster. They get to like 99% the speed of light, but those things have like hundreds of times, thousands of times more mass than they did when they started. Because all that energy went into not only making them go faster, but the mass goes up also. It's a cool, cool thing. That's why we can't get anything to go faster than the speed of light, because no matter how much energy we put in, it approaches the speed asymptotically. It's a real problem. It's a real problem, yeah?
So like how fast, like how close to the speed of light does it have to get moving before it starts increasing in mass?
That is a great question. Probably half. We can look at, let me look, see if there's a graph. It's like an actual graph. This is all very, very, very well understood by people who study this stuff. This is not. Oh, this is interesting. So this one has it in terms of, oh wait. Oh, it's funny, they graphed it upside down, or inverse compared to me. Which is fine. I think mine makes more sense than theirs, but we'll let it go. We'll let it go today. So if you look at this graph, they have speed here and they have kinetic energy here. And what you notice is, just cruising along, you get a nice linear relationship, and then all of a sudden, boom. You can see that over here is the speed, c, speed of light. And you can see that the speed of your object, which is a red, approaches it asymptotically. And it looks like it starts to get noticeable right around the half. So you gotta be going about half the speed of light in order for this to be noticeable. And half the speed of light is a ridiculous, I mean, this isn't, or the 187, that's not miles per hour, that's miles per second. So in order to get that to be miles per hour, we'd have to multiply by 3,600. So it's real fast. What is that? Someone very loud shoes. Do y'all see how this, like, it's a weird thing? Like, it's a super weird thing. This whole speed of light thing. It, like, weirds me out. Like, I can't think about it too hard, or I get really confused. But let's talk about a running race. Okay? Let's talk about a running race. And what you're going to do is you're going to run. Okay? And it only has to be like 100 meters. So what are you doing? It doesn't have to be miles, it can just be 100 meters, but whatever it is. Okay. So this is the finish line over here. Here's the starting line. We got some runners and we got some observers. Okay? So there's a runner. Here's a runner. And then here's the starter. So the guy with the starting gun is back here. And he's very happy to be the starter. Is that cool? But he's always interested in who won the race. Is that all right? So these guys run down. And over here, there's the spotter. He's at the finish line. Is that cool? Now, how does the starter know who won the race? He would have to see it, correct? Does that make sense? Or, if he doesn't see it, this guy could radio back. Does that make sense? Either way, it's going to be the same thing because radio waves and light waves travel at the same speed. All right? So, does the starter know who won the race when the race ended? And the answer to that is no. Now, he thinks he does because he saw them cross the finish line. He's like, that must have been the end of the race. But what actually happened is they crossed the finish line, then the light from them crossing the finish line had to get all the way back to him. So there's a delay between when the event actually happened and when he found out it happened. Does that make sense? But to him, he doesn't know any different because he can't experience it any differently than the light that he sees. Does that make sense? But we have another guy. And this guy is real fast. So here's our third guy, or our fifth guy here. And he's here. And he's standing at the finish line. Is that cool? And as soon as they cross the finish line, he's going to be right next to them. So he's going to see it really, really soon. He's going to run all the way back here and tell the starter what happened. But guess what? His speed is greater than the speed of light. So what happens? Blue and red start, they cross the finish line. Our real fast guy, let's call him our cyan runner, that's this color, cyan. Cyan runner runs back and he's like, hey, guess what? What's he tell him? Blue wins. Is that cool? But then what happens is the light from the actual, when they finished, gets here, and what does he see? He sees that blue wins. But he already knew that blue won. How did he know? Because this guy told him. But consider for a moment that this guy got back here and said, hey, guess what's going to happen? Blue's going to win. So what does it seem like this guy did? To him, to our starter, it looks like our cyan guy time traveled. Because he knew the outcome of a future event before it happened. In fact, what I find really interesting about this is that when our cyan guy gets here and say blue wins, the light from the finish line hadn't even gotten there. What light is there? What he sees at this moment is them here. So when cyan comes back and tells our starter, hey, blue wins, he actually sees them not even at the finish line yet. So it totally, to this guy, it seems like our cyan runner has actually gone back in time. Now, that can't happen because you can't travel faster than the speed of light. But what if you could? How interesting would that be? I don't know, I find it fascinating. Like this idea that light is finite in its speed messes up everything. I mean, it messes up everything. And I haven't even told you the worst part of it yet. I'm not going to tell you today because it'll confuse you more. All right. Guys good? All right, you ready? So we're going to use a simulation here to show us how things actually work in our solution. Now, this is the model, okay? This is the to scale, where if you were actually to try to look at something like the Earth and the Sun in their actual distance with their actual size, you can't see their actual size if you're trying to compare their actual distances, because they're too small compared to the distance they are away. Okay? For example, the Earth is 8,000 miles in diameter, but it's 93 million miles from the Sun. You see why you can't do that? So what we do is we look at the model because it's dimensional. So here's the Earth, here's the Sun. If I press play, what's it do? Goes around. How many days does it take to go around? Yeah, it's 365, right?
Effectively, though, like 365.25.
Yeah, it's and a quarter, right? So every year we go around, it's 365 days and a quarter day. So after 4 years, what are we going to have? Yeah, we're going to have a whole extra day. What do we do with it?
Go at the end of February.
Yeah, we shove it at the end of February.
There's not like every 100 years, there's no leap year, but it's divisible by 400.
Yeah, so
It's one.
Every century.
so it's a little bit more complicated, but you understand why. Now, tell me what you notice about the speed. Good. It seems like it's constant to me too. If I put a velocity vector on there, do we see? Oh, this is the worst thing about life. Like it never catches up. It's very unsatisfying. Very unsatisfying. Okay, but if you look at the velocity vector, does it ever change? Not really, right? Not really. We can do the same thing with the Earth and the Moon. Exactly the same, only different. Okay? How many days for the Moon? About 29. About 29 and a half days for the Moon. Maybe 27, it's hard to say. Okay? Is that look good? You guys okay with that? Now, I want you guys to look real close here. What do you notice is happening to the Earth as it goes around, as the Moon goes around?
Shifts like slightly wobble.
Yeah, do you see it shifting slightly? Do you see it wobbling back and forth? Why is it doing that? Okay? There's a Newton's third law of force pair there, right? So as it goes around, it's pulling the Earth out just as the Earth is pulling it in. If I put the velocity vector on there, you can see there's a tiny little green velocity vector on the Earth. Isn't that cool? But if I put the force vectors on, what do you notice about the force vectors? They're always equal, because it's Newton's third law of force pairs. Isn't that so interesting? You guys don't think it's interesting as me. I don't care that much, because it's fascinating. Again, very unsatisfying.
So are they like, they're rotating around the center of mass of like the Earth and Moon?
Yes,
system?
and that's actually, so this is a really important point. We're going to talk about binary stars in a minute. The two objects rotate around the center of mass. So the Earth, the Moon isn't really rotating around the Earth, it's rotating around the center of mass of the Earth-Moon system. It just happens to be within the Earth itself, because the Earth is that much more massive. So if you had two stars, for example, they don't really orbit each other, they orbit the center of mass of the binary star system. We'll talk about that in a minute. Okay. Watch this though. All right, what if you have all three here? So does the Moon go around the Earth? Yeah, it does. Right? But if the Earth is traveling at the same time that the Moon is going around the Earth, look how cute that is. Watch me put the path on.
Oh, yeah.
Isn't that so cool? This is the similar shape that we got when we took a bicycle wheel. Remember, we took a bicycle wheel and we drew what it looks like for 1 point on the bicycle wheel, right? 1 point, as the whole wheel rolls, if you just look at 1 point, it like kind of bounces around and then keeps going. That's what's happening here. So that's so cool. Anyway, that's enough of that. So, let's go back to this. And what we're going to do now is I'm going to adjust the mass of our stuff, and we're going to see what happens. So if I adjust the mass of the planet, watch what happens. I'm going to make it 2.5 times bigger, or 2 times bigger. What happened? Nothing, right? So the force was twice as big, but so was the mass, and so nothing happened to it. Remember, because when we go to calculate like the speed of objects or the orbital period of objects, the mass of the actual object cancels out of the equation, right? So nothing happened. But what's going to happen if I increase the mass of our star? Look what it did. Did it change the path? All right. It absolutely changed the path. And so what we're seeing now is that, what's that?
Looks like an egg.
It does look like an egg. So this is a mathematical oval. Uh-oh. Uh-oh. Yes. Oh no, it's gonna hit it. Don't hit it. Get around, get around, get around. Oh man. That sucked. All right. So, tell me about the speed. Is it always going the same speed?
Yeah.
Where is it fastest?
Closer to the.
Yeah, when it's closest, it's going to be fastest, and when it's furthest away, it's going to be slowest. Right? Let's see if we can get it to go away. Come on, you can do it, you can do it. Well, that's not much different. It's good enough though. So this is what we see, okay? Is that it's moving fast when it's close, and it's moving slow when it's far away. Is that cool? Now, this is something that if you were looking up into the night sky over many, many, many months, you might actually observe this, okay? You might actually be able to observe it and see what the situation was. So, this shape is called an ellipse, okay? Ellipses are very hard to draw because the degree of symmetry on an ellipse is high. All right. So let's say this is an ellipse. Is that cool? So we have a couple pieces to this. The line drawn across the long center, do you guys know what that's called? That's the major axis. Is that cool? All right, what about the one drawn through the center on the short side? How do we even know how to draw an ellipse? Well, there's two special points in an ellipse. They are out here toward on the center line, on the major axis, out here toward the ends. And these two lines these two dots are called they're called the focal points. Some people call them instead of calling them focal points, some people call them the foci. Some people call them the foci. Don't do that. Don't be one of those people. Okay. The reason they're actually called focal points, which is a really cool thing, is if I took this, I'm just going to take this shape here. Okay. I'm going to take this shape here of my ellipse. Okay. And I'm going to mirror it on the inside. I'm going to put silver on the inside to make it a mirror. If I were to take different beams of light and shine them in here straight like this, okay? They would all come in and reflect, go right through that point. That's where everything all the light rays get focused. That's why they call it a focal point. See how that works? All right? And there's one there, and there's one over here. So the focal points. So far, so good? So this is an ellipse. Now, the thing about this is that the part of this, we don't actually talk about the major axis very much, but we're going to talk about half of it. What do you think we call half of it? Okay? So half of it's called the semi-major axis.